Okay, everyone, this is the beginning of Chapter 5, and specifically the section 5.1, the derivative of exponential functions. First of all, I hope you quickly went through that logarithmic review and didn't have too big a problem with that worksheet. Some of those simplification logarithmic questions and evaluating some of those ln and e and logarithmic examples are quite challenging. But it's something we should be used to seeing at this level of math, and certainly in this course. And if you went through that review of logarithms, well, even great. I'm glad you could and do that. It's going to come in handy as we work through some of the work in Chapter 5. Okay, so Chapter 5 starts with derivatives of a special function called the exponential function. And we're going to be introduced to that. But the intro to Chapter 5 just talks about exponential growth with world population. We're seeing it currently with this COVID-19 situation, where these growths, we're trying to look and see how quickly things can grow, and we're looking for a leveling off or flattening the curve. You've heard that expression before. Certainly a lot of stuff we're seeing now in the news applies to sort of this analysis and discussion of what these graphs actually look like here. So we can use calculus for a lot of this and talk about the growth rate of a population, the growth rate of an infection as it relates to a population or amount over a certain amount of time here. Okay, so we see, and later in the chapter we'll talk about trigonometric functions. It's a good example of a trigonometric function, and talk about rates of change, and we'll combine some of these functions and talk about derivative rules in the rest of this chapter here. Okay, so our learning goals and success criteria, we're going to take a look at some of these goals in our chapter, and then how we're going to know we're successful with what we're going to do here with some of these items here. Okay, so feel free to take a look and read these things, and we'll get into today's lesson here. Okay, so in the review of logarithms, we talked about these two basic exponential functions. Really, when the base is less than 1, we follow the blue function, and when the base is greater than 1, we follow the red function. And notice that there's a horizontal asymptote at the line y equals 0. That's the x-axis. Okay? And if you want more information, there's a Wikipedia link here that'll just slide out of the way here, and it's embedded into my online course, and certainly on this slide. So yeah, feel free to, if you want to enhance your learning about exponential functions, feel free to read a little bit about these types of functions and curves. Okay, we also did some graphing. Okay, we did some graphing of these functions in Desmos. Okay, and I wanted to take a look at what these curves look like here. I'm going to call Desmos up here in a minute. So we've got y equals 2 to the x in red. We've got 3 to the x in blue, and this special one today, this e to the x. Okay, this is called Euler's number. Okay, okay, and we'll talk a little bit about the history of this particular curve and function here. So take a minute and go to Desmos, and I'm going to do that myself, and we'll get back to you in a second here. And I want you to graph these three functions here. Okay, so here's my first function, y, or f at x equals 2 to the power of x, and this is what it looks like. We've talked about this a little bit. I have an understanding of this from these exponential functions from 3U math, from advanced functions, I hope. I'm going to do something a little differently than what I asked in the lesson, though. Okay, I'm going to introduce you to this concept of a slider, and this allows us to graph multiple functions with different bases here, rather than just stack them all up, 2 to the power of x, 3 to the power of x, 10 to the power of x, and all these different things here. So I'm going to put in just an arbitrary variable here, k, and Desmos asks me if I want to add a slider for k, and I want to do that, absolutely. Okay, so I'm going to slide this around. Okay, I'm going to zoom out a little bit. I'm going to slide it to 2. Okay, and then slide it to 3 and see what's happening on the curve when I slide it to 3 and then to 4. So what I'm doing is I'm arbitrarily changing the base, okay, based on a variable here. Okay, so there's when it's, okay, 6 to the power of x, 6 to the power of x, 10 to the power of x. Now, I want to focus between 2 and 3 for this special type of function. So I'm going to change my, okay, I'm going to click on K, and I'm going to change it for the step pattern for between 2 and 3, and I'm going to do a step of 0.01 here, okay? So I'm going to click that off, and I'm just going to, okay, be able to drag that along here now. Now, this is, okay, our function, okay, at e, and what I want to do is even establish this next one here, at e to the x. Okay, so right in there, it looks like, okay, so the e to the x function is in blue. Okay, so if I just temporarily hide this, okay, for a second here, okay, and focus on, I hid my red graph here, okay, I left k alone here, and e to the x is in here. Now I'm going to reintroduce k to the x, okay, okay, and just drag this along so that it's really close to it. I have to zoom in. I want to try and match this function almost perfectly. So find the value of k that models the g at x is e to the x here. So it looks like I got to scroll down a little bit. Okay, it's still not good. I'm going to zoom in even more. Okay, and I want to have the blue function line up with the red function here. So good, good, good. Oh, that's getting pretty close right there. I don't think I can be any closer. Now my red's off a little bit. So it looks like it's around 2.7. I don't think I can be any better. Looks like it's almost going to go a little bit higher because it looks like my top's just off a little bit here. See that? Okay. So 2.71 almost looks perfect. Okay. So it looks like I have established, okay, a value for E, okay, and that's 2.71 by the looks of it. Okay, that's good enough here. Let's continue with, okay, my good work here. Let's see what else I've got here on this page. Okay, so there's my functions. Okay, and okay, Euler's number here is this special constant. Okay, it's somewhere between 2 and 3. Okay, and it has this special characteristic that we're going to talk about here, and that's this little result right in this area here. Okay, this is very important. Okay, and it's going to be the focus of, okay, the lesson here. This function, okay, is equal to its derivative here. Now, Euler's number, okay, is a pretty important irrational number in the sort of the science of math and the history of math here. Okay, it's a base, it's an exponential function, okay, that looks like this. Okay, these characteristics are very important. I want you to know these. These are the same characteristics as the exponential function that we saw earlier. Here it has a y-intercept. It's always increasing. There's no roots. Okay, there's a horizontal asymptote, okay, above the x-axis, so 0. Okay, at 0, y equals 0. And its end behaviors are such that this is the case here. Now I'm going to go back to, okay, to Desmos and take a look and see if we can find this derivative here and sort of show you how to do that here. But before I do that, I want to focus on, okay, the importance of this. So Euler's number, okay, Euler is another way to pronounce it here, is like like pi or like root 2 or irrationals. Very, very important. Okay, special numbers that had a long history in place in mathematics, and you're now introduced to very important exponential base here. That's approximately 2.7183. We're pretty close with 2.71, I think, and okay, it can be approximated with this limit. Okay, and it has this special characteristic that the function is equal to the derivative. Okay, so there is, again, a Wikipedia link for, okay, the history of, okay, our E constant. and I'll leave that for you guys to take a look at. Okay, so I'm going to go back to Desmos, okay, and I'll come back to finding the derivatives of these functions here in a minute. Okay, so keep in mind that we've just found, okay, a function here. We've just found, okay, a new function, okay, an exponential function that has a very, very important base. It's the base e, and it's constant. Okay, e is a constant, like pi is a constant. Okay, e is a constant value of approximately 2.718. Okay, so I'm going to change this up a little bit in Desmos and show you guys how to graph derivatives. Okay. So I'm going to, okay, just delete this function, go to my keyboard and go to my functions, okay, and go to my miscellaneous tab again and use this function right here. Now remember where my cursor is flashing, it's right here at g at x. So I'm going to, and then I'm going to use some brackets, okay, and I'm going to graph this one. Okay, so I've asked it to take the derivative, okay, I've asked it to graph a new function that happens to be the derivative of my original function. Okay, now I'm going to, okay, I haven't changed anything. My blue function still exists here. Okay, but what I'm doing by doing this is relating, okay, the original function with its derivative here, and I'm going to just try and find the same value here. Okay, so 2.71, and I can graph, in Desmos I can graph derivatives of functions and vice versa here. Okay, so that's the concept. Okay, that's the concept of this special function, okay, exponential function e to the power of x, or y equals e to the power of x. So we want to, okay, find some derivatives, okay, and I'm going to do that real quickly here and just show you how easy this is to do here. And this is actually a pretty fun unit section in the course, okay, for this type of work here. Okay, so if the derivative, okay, I want to find the derivative of the following functions, and y equals e to the power of x. Okay, so we just learned this rule today, so y prime equals e to the power of x. Very simple application. Okay, what if we have a composite function here, so e to the 3x. Okay, so y prime, or the derivative of y, okay, is the same as my function, but then I have to take the derivative of my composite function here. So I write that as e3 e to the x, e to the 3x, I apologize for that. Okay, so this is a chain rule application. If it's just a straightforward e to the x, the derivative is e to the x. If it's e, okay, to another function, it's the derivative of e. The derivative of the function is e to that function multiplied by the derivative of the function. Okay, this one. Okay, now I don't have this case here. So I have my 3 is a constant, so my y prime, okay, is still the derivative of my original function e to the x multiplied by 3. Okay, how about this one? Y equals e, and then the power is x plus 2. Now this is just a shift. Okay, this is just when I add 2 to my dependent variable x. Okay, that's just a, okay, that's a vertical shift. Okay, left or right. Okay, and when it's a plus 2, it's a vertical shift to the left. Okay, and it really doesn't change my derivative here. So my derivative is, okay, my derivative of e to some function is just e to that function, okay, and then multiplied by that function x plus 2. Now what's the derivative of that x plus 2 function? Well, that's just 1. So my derivative remains the same here. Okay, what about this function? Oh, I don't have y equals, okay, x over 2. Okay, well that's the same as y equals e to the 1/2 x. Okay, so my derivative then would be e to the 1/2 x multiplied by my derivative of 1/2 x, or I can write that as, okay, what happens when it's y equals e to the negative x? Okay, well, it shouldn't be a big deal here. Y prime would be negative e to the negative x. The negative shows up because it's the derivative of negative 1x. Okay, how about the next example here? I've got y, okay, and I've got an x squared multiplied by ex. Now, this is product rule. Okay, I've got two functions here, so I need a product rule. is just the application of my product rule. 2x times e to the x plus x squared times e to the x. Notice that there's a common factor. I can take out an x and an e to the x. That leaves me with 2 plus x, okay, which is the derivative of my original function here. Okay, does it make any sense? Okay. It's not a hard thing to find, certainly. It's not a hard thing to find. You just need to understand that this basic rule applies. Okay, this basic rule right here. Okay, and then watch for situations where we have to do the chain rule. Okay, let's do a couple more here. Okay, so here's the rule I just incorporated. If I have a function e to the f at x, then the derivative of that function y prime is equal to e to the f at x multiplied by f prime at x. Okay, so this one we just kind of did here. Okay. What have I got here? F at x equals 3x, so we'll change it back to black here. Okay, so that's 3 e to the 3x. Oh, this is a different one. Okay, f prime. So let's focus on my function here. This looks like it's e to the negative, x squared. Not quite here. Okay, 1 over x squared. That's another way to write 1 over x squared. About x to the negative 2. Okay, so I have then f prime is equal to e to the negative, sorry, I keep saying negative, and then multiplied by negative 2x to the negative 3. All right, this needs to be cleaned up a little bit. Okay, so I have so this simplified is, that's negative 2 e to the 1 over x squared over top of x to the power of 3. Okay, that's a bit of a tough one. Okay, now I have to find g prime. And g prime in this case, it's the same as my function. Now I have to find the derivative, multiply it by the derivative of my square root function. Okay, so that's two composite functions or two chain rules. That would be 1/2 multiplied by that's the negative 1/2, then multiplied by 2x. Okay, and I'm just going to leave that like that. Maybe clean this up a little bit. I'm fighting with my pens today. So this is the derivative of my square root function, which is so it's 1/2, and then the square root of x squared plus 1 to the negative 1/2, and then I have to take the derivative of the inner function here, and that's 2x. All right. Okay, these are a bit challenging here. There's going to be some homework questions for you to do these. Okay, so let's determine an equation of a tangent line given a function at a point here. Okay, so I'm trying to find, and I'll show this on a Desmos when I'm done here. Okay, so let's determine the equation of a tangent line here. Okay, so I need to find my point. Okay, so let's establish what my point is. Okay, when x is equal to 2 here, first of all. Okay, so e to the 2 over 2 squared. Okay, that would be e to the power of 2 over 4. Okay, so my given point is 0.2 e squared over 4. Okay, now at this point I want to talk about Okay, this e squared thing here. Remember, e is a constant. Okay, so we actually could go to our calculator and find out what e squared was. Okay, it would be an irrational number, and we divide it by 4. So we could actually get a decimal approximation for this. I don't want you to do that. I want you to leave it as is, the way it is written right here. It's the ordered pair 2, and then e squared over 4. That's a lot more accurate. If I get a decimal approximation, I lose some accuracy. So okay, I want to make sure that we're clear on that. We know how to do that. Okay, so now we've got to find y prime. Okay, and it looks like I need the quotient rule of these two part functions. Okay, the functions itself and the derivatives are actually pretty easy to find here. The resulting derivative equation, though, is going to be quite intense here. So my derivative function, okay, is going to be my, subtract my downs all over my little one squared here. Okay, so let's clean that up a little bit. Can we take out a greatest common factor? Okay, I think we can. We can take out an e to the power of x, okay, and an x, okay, and then I'm left with x minus 2 all over x to the power of 4. Now I can even further simplify that, okay, by getting rid of an x, okay, factoring out an x. Okay, now the next thing I do, if you remember these types of applications, is I evaluate my function at 2. So I need a value of my slope here, okay? So that's going to be, okay, well, it looks like that is, okay, 2 minus 2 is 0. Looks like my slope is 0. So that's a horizontal, okay, that's a horizontal line. Okay, so I'm just going to work over here in this space here. So that's actually a horizontal line. When my slope is 0, that's a horizontal line. I'm going to show you this in Desmos. I still do the rest of it though. Okay, I still want to find my equation of this horizontal line. So now I put in my values here. I found e to be e squared over 4, m was 0, x was 2, and then plus b. Well, it doesn't take you long to realize, okay, that b, okay, because e squared over 4. So my actual line here, y equals e squared over 4. And that's a flat horizontal line with a slope of 0 here. I'm going to show you this in Desmos, and I'll pause it here and show you what we've got here. Okay. Okay, here is this funny looking graph. Okay, and these will be crazy graphs here when we combine functions here and see a lot of strange looking graphs that we haven't experienced before here. Either way, that's fine. We can do these questions. Okay, so there's my function. Okay, I'm going to zoom in. My focal point is right around here. So I did change it from y equals to f at x. It just finds it a little bit easier to work with. Okay, there's my decimal approximation. Okay, right there. And that was what, e squared divided by 4, I think. Okay, so I can, okay, leave it at that. So, and I'm also going to plot that, okay? So I'm going to plot the point 2, and what did we say? E squared. I don't think I can, okay, label that. I can call that, okay, I'm going to call it P. And I'm just going to, oh, it doesn't like that. Oh well. We'll label that. Okay, so there's my point. Okay, and it looks like I've got, okay, a flat, the slope of that looks like it's almost a local minimum. Okay, and it would be a horizontal tangent line here. And I think if I even graph that, would see that, absolutely. Okay, good. So that's what we just did here. We found that equation. Give that line. All right, so, okay, that's a lot to digest and process here, I think, for learning a new concept here. I think I'm done with, okay, the examples. I don't know what else I've got here. We're going to leave these. Don't worry about these quite yet. We'll get to these. Not sure why these next two slides, the last two slides of this particular notebook file appeared, but don't worry about these. Okay, we'll revisit these later. I want you to stop right here and get to work on some of these homework questions. All right, good. Thank you, and have a good day.